bottom at the end, okay? This is it. And you can also just chat about it generally. Okay, so you are Mr.
Tawanda.
Okay, I'm ready.
I'd like to greet you all. Thank you very much for coming to my presentation. My name is Tawanda Mukanhairi. I'm doing my third year electrical engineering industrial stream. And I'm doing my Inservice training at SAO, South African Astronomical Observatory. Without wasting much of your time, I'd like to, well, ladies and gentlemen, welcome to the robotic rangefinder presentation. One question could come into your mind the moment I mentioned the rangefinder. What is really a rangefinder? By definition, a rangefinder is a device that measures distance from an observer to a target. So, the main objective of this project was to demonstrate and ensure more understanding on how to measure distance without any physical contact. I looked at radar technology, I looked at sonar technology, and I looked at infrared technology. All these three, I could use them to measure distance, but there was a problem. The cost. It was more costly to implement these technologies. So I shifted my mind. I shifted my idea to something else, ultrasonic technology, using the principles of sound that we learned in physics, which states that when sound wave hits an object, three things do happen. One, the sound wave is either reflected back as an echo. Two, the sound wave is either diffracted. And three, the sound wave is either absorbed by the object, but depending on the object's material, most of the sound wave is reflected back. So, looking at the time I send a signal, a sound wave to an object, and the time it takes to come back, I can use that time to calculate distance. So in my situation, I used an ultrasonic transducer for distance measurement. And I needed something better. I needed something more. So I needed the exact position of an object in a room within a slice. So I used the stepper motor for movement. There are many applications for ultrasonic technology in engineering in today's world. In astronomy, we can use ultrasonic sensors as distance proximity sensors. We need to make sure that the telescope does not reach certain areas, otherwise the user will end up damaging a multi-million-dollar device. We can actually measure the liquid level in a tank. And there are many applications that we can use ultrasonic technology in war warfare, in security systems, and the list is actually endless. And the real question comes, how is everything connected together? And how is everything communicating with each other? I've used a microcontroller, and in this situation, I'm using an Arduino board as the brain, as the main component of the system. I'm connecting the ultrasonic sensor to the microcontroller, which is the Arduino board in this case. I'm connecting to the digital pins of the Arduino board. And I create an algorithm that allows serial communication between the ultrasonic sensor and the Arduino board. I went on to connect the stepper motor to the Arduino board, but there was a problem. The Arduino board digital pins could only supply a maximum of 40 milliamps, but the stepper motor required 100 milliamps. So I had to develop a stepper motor driver using transistors, such that I could drive the motor from an external source. But still, I needed to present the position and the distance on a graph. So I used LabView for graphing. And I created an algorithm again that could allow my Arduino board to communicate with the LabView, so that I can present my graph on LabView. Now, as we all know, in every device that has been built already, or that is going to be built in future, there is always a secret behind it. There's always an idea behind it. So the question is, what is the secret behind the robotic rangefinder? For distance measurement, I'm using an ultrasonic transducer. It has a transmitter and a receiver. I'm sending a 40 kilohertz pulse from the transmitter, and I'm receiving an echo, a 40 kilohertz echo on the receiver. So I'm measuring the time to send and to receive the echo back. And that time, I'm using it to calculate distance. Using a simple formula, distance equals speed times time. We know the speed of sound in air. which is approximately equal to 343.2 meters per second. Others, they say 340 meters per second. So I have the speed, I have the distance, I have the time, I can calculate the distance. But still, yes, I have the distance, but I needed something more. I needed the actual position of the object on a graph. I needed something more. So I turned my mind to trigonometry. So using the simple formulas of trigonometry, I could create an algorithm that could actually give me, but I have the distance. But still, I need x and y values. So how could I get x and y values? The stepper motor gives me the angle per step, which is 1.8 degrees per step. So now, my algorithm would allow me to get x and y values. So I could get an exact position of the object in a room using the trigonometry formula. So how is everything represented on a graph in LabVIEW? The graph shows like that. To my right is the graph showing the exact thing in real time. The device takes readings in real time and plots in real time. So, ladies and gentlemen, to conclude, I would like to say that ultrasonic technology is useful in today's engineering world, especially where there's need for distance measurement without any physical contact. So using the simple principles of sound, one can actually measure the distance of an object from the observer using ultrasonic sensors. Please allow me to show you the device in motion, the robotic rangefinder in motion.
Okay, now I'm scanning the whole room. So the stepper motor is going to take 200 steps. Is equivalent to 360 degrees, which is 1 revolution. As you can see. Okay. Going to home position there. Okay, I'm scanning again.